Welcome to our channel, and today we are going to help you understand the paper-efficient streaming language models with attention sinks. Summary: the preprint titled Efficient Streaming Language Models with Attention Sinks by Guang Xiao and colleagues from MIT, Meta AI, and Carnegie Mellon University delves into the challenge of deploying large language models, LLMs, in streaming applications like multi-round dialogues that expect lengthy interactions. They identify two main issues: the substantial memory consumption during the decoding stage from caching previous tokens' key and value, states, and the inability of LLMs to process texts longer than their training sequence length effectively. To overcome these challenges, the authors observe a phenomenon called attention sink, where maintaining the KV of initial tokens significantly improves the performance of window attention models, which cache only the most recent tokens for efficiency beyond their cache size. They find that attention sinks, even if not semantically important, act as a focal point for strong attention scores. Building on this, the authors introduce Streaming LLM, a novel framework enabling LLMs trained with a finite attention window to handle infinite sequence lengths without requiring additional fine-tuning. Their approach allows popular models like Llama 2, MPT, Falcon, and Pythia to work with up to 4 million tokens and beyond. Notably, they also discover that inserting a placeholder token as an attention sink during pre-training enhances streaming deployment. In the streaming context, Streaming LLM surpasses existing baselines, notably outperforming the sliding window recomputation approach by a factor of up to 22.2 times in terms of speed. The authors make their code and datasets available online. The paper introduces the concept of LLM streaming applications and ponders the feasibility of using an LLM for infinite-length inputs without compromising efficiency or performance. The text provides an overview of various approaches to handling attention mechanisms in autoregressive large language models, LLMs, for processing long sequences of data, and introduces a new methodology called Streaming LLM, A. Dense attention requires OT2 time complexity and suffers from poor efficiency and performance on longer texts as the cache size increases with longer sequences. B. Window attention is efficient in inference but fails when the initial tokens are evicted because it only caches a fixed number of the most recent tokens. C. Sliding window with recomputation offers good performance on lengthy texts, but it is slow due to its OTL² complexity from recalculating attention in a quadratic context for each new token. D. Streaming LLM, the proposed method, maintains attention sync tokens to provide stable attention computation, avoiding issues previous methods faced with very long texts. It combines these attention sinks with recent tokens to enable the processing of infinite text lengths without additional tuning. The text cures different models using Perplexity, PPL scores from the Llama 213B model, with Streaming LLM showing a PPL of 5.40, indicating efficient and stable language modeling for long texts. Additionally, the text highlights challenges faced by transformer-based LLMs related to caching and processing input streams, such as excessive memory usage and latency. It also mentions that current models struggle with extrapolation abilities beyond their pre-training window size, leading to diminished performance. It concludes by explaining that initial tokens often become attention sinks that accumulate a disproportionate amount of attention, regardless of their relevance, due to the softmax operation requiring attention scores to sum to 1. Streaming LLM addresses this by preserving attention sinks alongside a sliding window of tokens, achieving stable performance on long text without fine-tuning. Various model architectures are mentioned as having been tested with Streaming LLM. The text discusses the attention patterns and pre-training strategies of large language models, LLMs, specifically referring to a visualization of attention logits from the Llama 2.7b model over 256 sentences. The key observations are: 1. Early layers of the model focus on nearby tokens, local pattern. 2. In higher layers, the model heavily focuses on the first token, suggesting the need for only one attention sync token for streaming deployment. The authors introduce a Streaming LLM framework designed for processing text much longer than the training window size, without increasing the attention window size or enhancing memory on long texts. This framework allows for a speedup of up to 22.2x compared to baseline methods and confirms that a single learnable token can act as an attention sink during pre-training, enabling effective streaming performance without the need for multiple initial tokens. Related work is categorized into three areas: length extrapolation, adapting models trained on short texts to handle longer texts. Methods like relative position encoding and the EB approach have been tried without achieving infinite extrapolation capabilities. Context window extension, expanding LLM attention windows. While several efficiency-focused solutions have been proposed, they have limitations in terms of how much they can extend context windows. Improving LLM's utilization of long text. Techniques to enhance the capture and use of content within the context, rather than just extending the size of the input the model can take. The authors clarify that progress in one category does not imply progress in the others. Their method, Streaming LLM, aims to apply LLMs to indefinite length inputs without expanding the attention window or memory usage on long texts, and can be integrated with other techniques for improving the utilization of long texts. The text discusses the performance of large language models, LLMs, with different attention mechanisms when dealing with texts of 20,000 tokens. The findings presented include 1. Dense attention in LLMs fails when the input length exceeds the size of the pre-training attention window. 2. Window attention becomes ineffective when the input length goes beyond the cache size, causing the loss of the initial tokens. 3. Streaming LLM, however, shows consistent performance and closely matches the baseline of a sliding window with recomputation in terms of language modeling perplexity. 4. Despite successes in some areas, effectively using long contexts within LLMs remains a challenge. 5. Streaming LLM aims to effectively process the most recent tokens for smooth streaming applications of language models. 6. The concept of attention sinks is introduced to understand why window attention fails, leading to high perplexity in language modeling. 7. Initial tokens, despite their semantic value, are found to have special significance because of their position, and their removal skews the attention distribution. 8. The text posits that initial tokens serve as attention sinks, a role required due to the nature of the softmax function in attention mechanisms. This suggests that attention is sometimes unduly allocated to certain tokens simply to satisfy the mathematical constraints of the attention process, rather than because of their relevance. 9. The phenomenon has parallels with quantization outliers, and softmax off by 1 has been proposed as a potential solution. Overall, the text indicates that managing attention over very long sequences is a challenge for LLMs, and Streaming LLM is a proposed approach to address this challenge. The text discusses the performance of autoregressive language models, LLMs, like Llama 2, MPT, Falcon, and Pythia, in processing long text sequences. When these models use window attention, focusing on a recent set of tokens without including initial tokens, their performance, measured by perplexity, worsens. Perplexity is a measurement of how well a probability model predicts a sample. A lower perplexity indicates better performance. The study finds that restoring 4 initial tokens alongside the recent tokens significantly improves model performance, even if these initial tokens are placeholders like line breaks. Cache configuration notation X plus Y is used to denote the addition of X initial tokens with Y recent tokens, and the research presents how different configurations affect perplexity. The researchers argue that autoregressive LLMs use initial tokens as attention sinks because these tokens are visible to all subsequent tokens in the sequence, making them more easily trained for this purpose. The paper details that during pre-training, the LLMs do not consistently start with the same token, leading them to use multiple initial tokens as attention sinks. The authors propose that using a stable, learnable token as the consistent starting point during training could allow the models to concentrate attention more efficiently. In Section 3.2, the authors propose a method for LLMs to stream text by using a rolling KV cache with attention sinks. This system reintroduces some starting tokens key value, KV pairs, into attention computation without needing model fine-tuning. This cache is divided into 2 parts. One stabilizes attention computation with 4 initial tokens, while the other retains recent tokens crucial for language modeling, The design of the rolling KV cache is adaptable to existing autoregressive language models and handles positional information differently to maintain efficiency. In contrast to remembering the original positions of tokens, the cache assigns new positions to the tokens based on their location within the cache. This is particularly important for compatibility with positional encoding methods like ROPE and alibi. In summary, the text highlights how adding initial tokens to the attention mechanism of LLMs can drastically improve handling long text sequences and introduces a cache design that can enhance performance without retraining the model. The text discusses a study involving pre-training language models, LLMs, with an emphasis on how attention mechanisms handle the distribution of attention across tokens. Researchers compare three distinct attention approaches in pre-training. 1. Vanilla attention, which requires several initial tokens to achieve stable streaming perplexity. 2. Zero sync, which appends a zero token and slightly improves performance, but still depends on additional initial tokens. Learnable sync token, a novel technique that introduces a trainable token that serves as a sink for excessive attention scores, significantly stabilizing streaming perplexity with just this token. Experiments demonstrate that both zero sync and the model with the learnable sync token reduce the need for multiple initial tokens as attention sinks, with the latter being especially effective. The paper suggests using a learnable sync token in the pre-training of future LLMs to optimize streaming performance. The study also evaluates Streaming LLM, a language model, on various recent models across different families, Llama 2, MPT, Pythia, Falcon, to ensure robustness of the results. Using text from the PG-19 test set, which consists of long books, they observed that Streaming LLM can achieve perplexity comparable to the best baseline sliding window with recomputation when dealing with texts up to 20,000 tokens and manage texts over 4 million tokens across different model scales and families. This highlights the potential of Streaming LLM in handling very long texts effectively. The text discusses a study on streaming large language models, LLMs, for processing super long texts of up to 4 million tokens. The study first describes the use of Streaming LLM and its stable perplexity across various LLM families and model scales when tested on very lengthy texts. A perplexity fluctuation was observed when transitioning between books from a concatenated test set of 100 books from the PG-19 dataset. In section 4.2, the study presents results from an experiment designed to assess the effectiveness of introducing a sync token in pre-training of Streaming LLMs. Two 160 million parameter models were trained, one with a sync token and one without it. Both models underwent identical training processes using the Pythia 160M codebase and were trained on NVIDIA A6000 GPUs using the Pile dataset, with a reduced batch size but otherwise standard Pythia training configurations. After 143,000 training steps, both models showed similar convergence trends. Further analysis showed that including a sync token during pre-training did not harm overall model performance on a variety of NLP benchmarks, such as ARC, HelloSwag, Lambda, OpenBookQA, Pika, and Winogrand. The performance data indicate that the model with the sync token performs comparably to the vanilla model. The study also explores streaming performance, demonstrating that models trained without a sync token required multiple attention sinks to achieve stable streaming perplexity. In contrast, the model trained with a single sync token showed satisfactory streaming performance. Finally, attention visualization results indicated that models trained with a sync token focused their attention more consistently on the sync token across different layers and heads. This finding suggests that using a sync token is an effective attention offloading strategy that enhances the streaming performance of the model. The text includes a specific example using register content, lines that demonstrate the input content provided and the desired output in the context of StreamEval, with the intention that the information should be remembered. The text focuses on the performance of language models, LMs, on question answering tasks, with an emphasis on a feature called the sync token, and on streaming attention models named Streaming LLM. A visualization, Figure 7, compares the attention patterns of models trained with and without a sync token. It notes that without a sync token, models tend to focus on local context in lower layers and on the initial tokens in deeper layers. With a sync token, models show clear attention to the token across all layers, indicating that it can collect redundant attention and decrease focus on other initial tokens, which is beneficial for streaming performance. Performance on the ARC AI2 Reasoning Challenge datasets is reported in Table 5. When the dense attention method is used, it runs out of memory, while window attention shows poor accuracy. In contrast, streaming LLM achieves comparable accuracy to the one-shot baseline and maintains it well even in streaming scenarios, where the inputs are lengthy. Subsequently, the text introduces a new dataset called Stream Eval, catering to realistic scenarios where questions relate to recent information. It demonstrates that streaming LLM can maintain reasonable accuracy with input lengths up to 120K tokens, unlike the dense and window attention methods that fail at certain length thresholds. Additionally, streaming LLM is shown to complement other context extension techniques, effectively handling longer contexts by expanding the maximum cache size. Ablation studies on the number of initial tokens used in streaming LLM reveal that having 4 initial tokens suffices to achieve the desired effect on streaming perplexity, whereas adding more only results in marginal improvements. This validates the choice of using 4 initial tokens as attention sinks in streaming LLM. The text provides an analysis of the streaming LLM framework's performance in comparison to a sliding window with recomputation approach for handling large language models, LLMs, in streaming applications. The key points from the text are: 1. Figure 9 shows the performance of various approaches on the Stream Eval benchmark, evaluating average accuracies, latency in milliseconds, and memory usage in gigabytes based on varying cache sizes, attention window sizes. Streaming LLM notably improves speed up to 22.2 times per token with similar memory usage to the baseline sliding window with recomputation. 2. Cache size impact on perplexity is addressed, and surprisingly, increasing cache size does not consistently reduce perplexity, suggesting that LLMs may not fully leverage the entire context available to them, indicating an area for future enhancement. Table 6 compares perplexity across models with different cache configurations, showing that increasing the cache size does not lead to a uniform decrease in perplexity across all models. Efficiency results benchmark decoding latency and memory usage of streaming LLM against the sliding window with recomputation baseline. Figures demonstrate that streaming LLM offers a linear improvement in decoding speed as cache size increases, while the baseline exhibits a quadratic rise in latency. Streaming LLM thus achieves significant speedup while maintaining consistent memory usage. 5. The conclusion emphasizes the urgent need for deploying LLMs in streaming applications. Despite challenges such as efficiency limitations and decreased performance on longer texts, the streaming LLM, a simple and efficient framework, is introduced as a solution that allows LLMs to handle unlimited text lengths without fine-tuning by using attention sinks with recent tokens. The text also suggests that pre-training models with a designated sync token could advance streaming performance. Streaming LLM essentially decouples pre-training window size from text generation length, facilitating the streaming deployment of LLMs.